That's
All right, yeah.
Oh, that's my
that's great. You're doing. Yeah, that's the one.
But you were supposed
Yeah,
to.
I was supposed to do that.
what did you have? I'm so sorry. It would have been yes on my desk.
Does this work? Yeah. Testing? Oh, great. All right. Okay. Huh.
Yeah, let's see. Can you make your screen again?
Oh, yeah, of course.
Okay, hi everybody. Those of you on Zoom and actually in the room, we'll get started in a few minutes. We're just making sure everything on Zoom is working okay. Those of you on Zoom, can you hear us okay? And Chen, can you say?
Yeah, of course. Can you hear me?
Yes, we hear well.
Oh, great.
Great, wonderful. And you can see the screen, I assume.
Yes,
All right.
everything is good.
Okay, thank you. Thank you, Yoram. All right, good. Well, it's my pleasure to introduce this Astrophysics Symposium. So we're going to have 3 talks this morning. The format is that we'll have the talks will be 45 minutes long. We'll have time for questions for about 10 minutes and 5 minutes of break in between. Let's see how well we can stick to that schedule. But I think there's plenty of buffer time so that we can, definitely stick to the 1 hour per talk schedule. So our first speaker is ChangHoon Hahn. He goes by Chang. From Princeton University, and he'll be telling us about probing dark energy and neutrinos with 40 million galaxies. Take it away.
Thanks so much, Rena. Hi, everyone. I'm Chang. I'm a postdoc at Princeton University. And today I want to talk to you about how we can address fundamental questions on the nature of dark energy and neutrinos with the millions of galaxies that we'll observe with upcoming galaxy surveys like DESI and PFS that I've led. More importantly, I want to show you how I'm going to extract all of the cosmological information from these surveys using simulation-based inference and machine learning and double the constraints that we can, precision of the constraints we can place on dark energy and neutrinos. So I just want to point out my figure in the background here, and this is just a glimpse of what I'm going to be talking about. Each point in this figure is a galaxy that's already been observed by DESI. So let me start with giving you a brief introduction or overview of what I'm going to talk about, since I'm going to be covering quite a broad range of topics today. So first, I want to give you a quick introduction on how to extract cosmological information from galaxy surveys. And I'm going to tell you about the standard analyses that we use to place constraints on dark energy and neutrino mass. Then I'm going to show you my work in illustrating that we can double the cosmological information from galaxy surveys by going beyond these standard analyses. Afterwards, I'm going to talk about how we can actually do these analyses on observations using simulation-based inference and machine learning. And I'm going to talk about my recent work in applying this to existing observations. Then, lastly, I'm going to give you a quick update on the status of the next generation galaxy surveys like DESI and PFS that I've led. All right, let's get started. Let me start with a quick introduction. So cosmology at this point has converged to a standard model that we call lambda CDM. And this model has been remarkably successful at reproducing all of the different cosmological observations we've made over the last few decades. And according to this model, the story of the universe begins with the Big Bang. There's a period of rapid exponential expansion of the universe that we call inflation that seeds the initial density fluctuations in the primordial plasma. Then after recombination and decoupling of the photons from this plasma that become the cosmic microwave background that we observe, there's a period where the baryonic and dark matter of the universe gravitationally form the stars, galaxies, and the larger structures that we observe. Then around 10 billion years since the Big Bang, there's a period, the universe gradually enters this period of accelerated expansion that's driven by dark energy. So despite giving us this complete story of how the universe, the history of the universe, and reproducing all of our cosmological observations, the main pillars of the lambda CDM model are not well understood. So this is a really exciting time for cosmology because as cosmologists, we now have a glimpse of everything in the universe that we don't understand. And we have a number of major experiments that will allow us to address all of these fundamental questions about the universe. In this talk, I'm primarily going to focus on dark energy, which in addition to driving the accelerated expansion of the universe, also accounts for 68% of the total energy density of the universe. So one of the most promising ways of probing dark energy is using spectroscopic galaxy surveys, like the one I'm showing you here, which is the Sloan Digital Sky Survey in New Mexico. And what these surveys provide is they measure the angular positions of galaxies, like the green box that I'm showing you here, and they also measure the spectra of galaxies. This is spectra from the Sloan Digital Sky Survey, and you can see all of these detailed features here, like the emission lines. So you can use these features, compare them to their rest frame wavelength, and use Doppler shift to measure the redshift. And since redshift measures the velocities of the galaxies along the line of sight, in an expanding universe, this velocity is proportional to the distance of the galaxy from us. So that means we can use the angular positions and the redshifts to produce detailed three-dimensional maps of galaxies like the one I'm showing you here. This is a map from the Sloan Digital Sky Survey made from observations by Michael Blanton. And again, each of these points are galaxies observed by SDSS. So in addition to providing those beautiful maps, the distribution of galaxies also encodes a tremendous amount of information on cosmological information, particularly on the growth of structure. So the redshift that we observe, it actually has two components. The first component is the redshift from the cosmic expansion that I mentioned earlier. Then there's a component that comes from the peculiar velocities of galaxies. So if we didn't have this second component, the galaxy distribution would look something like this. And this is what we call real space. This is the distribution of galaxies. And so once we add this peculiar velocity component, this distribution gets distorted to look something like this. And we call this redshift space. So we can actually use these distortions to probe cosmological information. So there's two regimes of these distortions. The first are these long elongated structures that kind of look like fingers of God pointing at us. And this is caused by the random velocities of galaxies that are in virialized structures in the universe. Then there's another regime of these distortions, which is on larger scales. So if you focus on this overdensity here, and if I flip to from real space to redshift space, I'm going to do it again, you can see that there's a sort of squashing along the line of sight. And this is caused by the Kaiser effect. And this is from the coherent motions of galaxies that are gravitationally attracted to large scale structure. So this effect allows us to probe structure formation in the universe. So if you do the math, you can write down the overdensity of galaxies in redshift space in terms of the overdensity of galaxies in real space, plus this additional term that depends on the growth rate of structure and the overdensity of matter. And I just want to remind everyone, this is in Fourier space. So K here represents the Fourier mode. So typically when we look at the distribution of galaxies, we don't look at the full distribution and we look at summary statistics of the distribution. So we typically analyze the galaxy power spectrum, which is the Fourier transform of the 2-point correlation function. If that doesn't mean anything to you, what it does is it measures the excess probability of finding a pair of galaxies at a certain separation above a random distribution. So if we write down the galaxy power spectrum in redshift space, we can also see that it depends on the growth rate of structure and the matter power spectrum. And typically, we parameterize the matter power spectrum, the amplitude of it, as with the cosmological parameter sigma 8. So with the galaxy power spectrum, we actually measure this combination of the growth rate of structure and sigma 8. So in practice, what we do is we make these measurements of the galaxy power spectrum. I'm showing you two measurements from the SDSS collaboration at two different redshifts. So we do this in multiple different redshifts and then infer the F sigma 8 or the growth of structure from these measurements. And then afterwards, we can compare them to predictions of different cosmological models. So I'm showing you here the growth of structure as a function of redshift for predictions of the standard lambda CDM cosmology in the black solid line, and two alternative cosmological models, NDGP, which is a well-studied modified gravity model, and quintessence, which is a dynamical dark energy model. I'm not going to go into details about the alternative models here. And we've made a number of different constraints already on the growth rate of structure for different redshifts. However, you can clearly see that there's still significant room for improvement, especially if you want to be able to precisely distinguish between these different models. And just to give you a glimpse of what I'm going to show you in this talk, since it's early in the morning, I want to keep you guys engaged. In this talk, I'm going to show you how we're going to go from this to the orange constraint that you see here. So another key cosmological information that's in the galaxy distribution is information on the mass of neutrinos. So as most of you know, neutrino oscillation experiments established that neutrinos have mass, and they've placed a lower bound of 0.06 eV on the total neutrino mass. And however, these experiments, they don't precisely measure the total neutrino mass. And we care about this because it'll provide key input for physics beyond the standard model. For example, a precise enough measurement would allow us to distinguish between the inverted and a normal hierarchies of neutrino mass. Fortunately, galaxy distributions allow us to measure this neutrino mass because massive neutrinos suppress the growth of structure on small scales below their free streaming scale, but they contribute to the clustering of matter on large scales. So I'm showing you two snapshots from two simulations. On the left is a simulation with massless neutrinos, and on the right is a simulation with massive neutrinos. And you can visually clearly see that there's significantly less small scale clustering when you have massive neutrinos. More quantitatively, we can look at the effect of massive neutrinos on the power spectrum. So I'm showing you here the fractional effect of different amounts of neutrino mass. So the more massive, the larger the suppression on small scales. So again, I just want to point out that this is in Fourier mode. So this smaller values are larger scales, higher values are small scales. So what we can do from the galaxy distribution is measure this scale-dependent imprint and then place constraints on the sum of neutrino masses. In fact, the current tightest constraints actually come from cosmology, from combining the constraints from the cosmic microwave background with large-scale structure. Right now we have an upper bound of 0.13 EV. And I just want to point out that recently from laboratory experiments, the Katrin collaboration placed an upper bound of 0.8 EV. So cosmology provides a really competitive way and a complementary way of placing constraints on the sum of neutrino masses. And again, to give you a glimpse of what I'm going to talk about here, I'm going to show you how we're going to go from this upper bound to the orange constraints that, in this talk. Okay, so let me give a quick recap for everyone. Galaxy distributions from galaxy surveys allow us to probe cosmological information that we can use to constrain the nature of dark energy and the mass of neutrinos. And this is a really exciting time because over the next decade, we have a lot of different major surveys that will probe an unprecedented volume with galaxies. And this is all for the purposes of constraining dark energy and neutrinos. However, all of these exciting surveys are going to exploit less than half of the total cosmological information that's available in the observations if they use the standard analyses. And that's because standard clustering analyses focus on the power spectrum, and they also focus on analyzing large linear scales. So this is, again, the measurements of the galaxy power spectrum in the 2 redshift bins from SDSS. And what I mean by linear scales is the linear regime where linear perturbation theory is accurate. So the assumption that the density fluctuations are small hold up. And current analyses only extend their K max value to 0.2 due to the limitations of modeling this regime. But of course, there's cosmological information beyond this limit. And there's also cosmological information in higher order clustering statistics. So I talked about the power spectrum, but what I'm showing you here is the bispectrum. And the bispectrum measures the excess probability of finding triangle configurations of galaxies over a random distribution. And this is what the bispectrum would actually look like if you took every different triangle configuration and then plotted their amplitude. I just wanted to show this. There's no, just give you an idea. But intuitively, let me demonstrate why there should be information in higher order statistics. Here's 2 distributions that you can visually see are very different from one another. If you go ahead and measure their power spectrum, they look identical. Of course, if you measure any of the higher order statistics, then you'll immediately see that these are very different distributions. So at this point, you might be wondering, well, how much cosmological information is actually available beyond the standard analyses with the power spectrum? Well, to answer this question, I construct the Molino Suite of simulations. These are 75,000 galaxy simulations that's specifically designed to quantify the information content of higher order clustering statistics. So the way I constructed these is I started with a n-body simulation, the Quixote simulation. I'm showing you a snapshot of all of the dark matter particles here. I identify the dark matter halos, which are the virialized structures of dark matter, and using a friend-of-friend algorithm. And afterwards, I populate these halos with halo occupation distribution framework, or HOD. I don't think Frank's here, but Frank would know all about it. But essentially, it's an empirical framework that allows us to populate halos with central and satellite galaxies as a function of the properties of the halo, like its mass, and free parameters called the HOD parameters. So the Molino Suite provides all of the ingredients to do Fisher matrix forecasts to derive how constraining different clustering statistics will be. Yeah.
Are you building in any correlations when you populate in this way, or you're not?
In which part?
when you populate them this way.
Yeah.
Are you introducing any correlations, like third order and so on?
Oh, you mean in the clustering?
Yeah.
So the short answer is yes, but these models will be based on our understanding of how galaxies connect to our halos. So it's not we're not feeding in information about the clustering explicitly. So again, what Molino provides are the ingredients for a Fisher matrix forecast. So primarily, it includes the 15,000 simulations to estimate the covariance matrix of your different summary statistic or your clustering statistic. And it also includes 60,000 simulations to estimate the derivatives of the statistic, no worries, with respect to the different 11 different parameters. So the parameters include 6 cosmological parameters, and then 5 additional HOD parameters. So using this ingredient and plugging it into this equation here for Fisher matrices, we can derive the following constraints. So I'm showing you here, this is a very busy plot, but the top set of panels are constraints on the cosmological parameters, and the bottom set of panels here are for the HOD parameters. And the different colors, the blue is the constraints for the power spectrum, so the standard analyses, and the orange is for the power spectrum combined with the bispectrum. So you can already immediately see that adding the bispectrum dramatically improves the constraint. So if we focus just on the cosmological parameters, we can see that we improve the constraints on these parameters by a factor of 3 with the bispectrum. And for neutrino mass, the improvement is even more significant. We actually find a factor of 4 improvement on the total neutrino mass. And the other thing we can look at is how the constraints depend on what scale we go to, so the K max value. So I'm showing you here the 1 sigma constraint for the marginalized posteriors for each of these individual parameters. And you can see, I've labeled here the current limits of analyses. You can see that the constraints improve as you go to smaller and smaller scales. And this improvement is even more dramatic if you include the bispectrum. So thanks to these simulations like Quixote and Molino, we've identified now many different promising clustering statistics that go beyond the power spectrum. So I don't have time to go into all of these in detail, but these are some of the ones that I've worked on: wavelet statistics, skew spectra, reconstructed power spectrum, and the marked power spectrum. These all improve constraints over the power spectrum. So now you're probably wondering, what's stopping me from using all of these higher order statistics and analyzing nonlinear scales? Well, the devil's in the detail of how you do these analyses. So one of the main challenges right now is the fact that analytic models of galaxy clustering are based on perturbation theory. And so they're inaccurate on nonlinear scales and also for higher order statistics. So this is a figure from Ivan Chudaykin and Misha Ivanov's paper that shows you the bispectrum as a function of scale. And the error bars here indicate the uncertainties in this measurement. So on large scales, these come from just the sample variance of the measurement. On small scales, they're entirely dominated by theoretical uncertainties. So you can already see that at K of 0.1, you're dominated by theoretical uncertainties for the bispectrum. And of course, there are no analytic models from perturbation theory available for many of the promising summary statistics that I've showed you, like the wavelet moment statistics, kth nearest neighbor, minimum spanning tree. So you wouldn't be able to write down a perturbation theory model for these. The other challenge is that observations are messy. So I'm showing you here the angular distribution of galaxies in the SDSS observations. And you can see there's these giant holes in the survey. There's these claw marks that are from imaging. So all the cosmological analyses have to account for all of these effects. Another observational effect that I've spent a lot of time thinking about are fiber collisions. So I'm showing you in the background here, this is an aluminum plate that goes into the focal plane of the Sloan Digital Sky Survey. There's these little holes here, and this is where actually the team members would manually plug in the fibers that go into the spectrograph to measure the spectra. So you can imagine if there's a physical hole that you have to drill, then there's a limit to how closely you can put two fibers next to each other. So if you're observing in a dense part of the sky, this limitation would have an imprint on the measured statistic. And this is what I quantified a couple of years back using a number of simulations. So this is looking at the fractional residual of the power spectrum. So the different colors are the effect of fiber collisions. And I've put for reference the sample variance, so statistical uncertainty. And you can see that even at K of 0.1, which is within current analyses limits, the effect of fiber collisions already exceeds the statistical uncertainty. And so there's a number of correction schemes available for the power spectrum, like the one I've worked on, but they all come with some caveats in implementing them. And of course, there's currently no correction scheme available for higher order statistics or any of the promising statistics beyond the power spectrum. So let me summarize here all of the challenges that we're facing in analyzing statistics beyond the power spectrum. We have to model the nonlinear scales. We have to model the statistics beyond the power spectrum. And lastly, we have to account for observational systematics. However, we don't have to take an analytic modeling approach. We can instead use simulations and take a simulation-based approach to this, and then address each of the three challenges. So in terms of modeling nonlinear scales, if we use M-body simulations, those simulations are much more accurate at modeling those smaller scales. And in terms of higher order statistics beyond the power spectrum, with simulations, we can analyze any summary statistic that we can observe on the data, measure on the observations, on the simulations. And lastly, in terms of the systematic effects, we can include all of the effects in our forward model and simulate them. And we don't even have to reinvent the wheel because all of these collaborations already have forward models developed that they use to test the robustness of their analysis, so we can use these tools to develop these simulations. So now the main challenge is, how do we go from these forward modeled simulations to the cosmological parameters? Because if we were to use the standard approach and replace the likelihood with running a simulation, that means we'd have to run hundreds of thousands of simulations, and cosmological simulations are very expensive, so this would be prohibitive. So this is where I'm going to tell you about simulation-based inference and machine learning techniques that we can use to do this. So let me first go to a much, much simpler problem than analyzing the distribution of galaxies, which is very high dimensional, and talk about a one-dimensional observation X and a one-dimensional parameter space theta. I'm showing you here the joint distribution of theta and X. And this distribution actually encodes all the information that we're interested in, like the likelihood and the posterior, because the likelihood is this distribution conditioned on some specific parameter value theta prime. And the posterior is that distribution conditioned on some specific observation X prime. So if we have a forward model, what we effectively have is a way to sample this joint distribution. So by plugging in different values of theta, and the observations that we get are samples of this joint distribution. So with this forward model, we already have a way of inferring the posterior, and that's the simplest simulation-based inference method, which is called approximate Bayesian computation, or ABC. So the way it works is really straightforward. Step one, you sample a parameter from your prior, and then the second step is you run your forward model to generate your observations. And you repeat this over and over and over again. And then you slowly populate this joint distribution. And if you do this enough times, you can compare it to the actual observations that you've made, and then only keep the simulations that are close to the observations. Then if you look at the distribution of parameters of those simulations that are left, that is the posterior. So that's ABC right there. So of course, in the real world, instead of using the full distribution of galaxies, we instead use summary statistics, which are much lower dimensional. And we don't use rejection sampling where we throw out all of the simulations that we've run. We instead use something more efficient, And that's actually what I did in a couple of years back, where we applied simulation-based inference for the first time on galaxy clustering, and we inferred the HOD parameters using ABC with population Monte Carlo. And this is actually work done with folks that were at Yale at the time, Andrew Heron and Duncan Campbell. But as you can imagine, even with more efficient sampling methods, ABC requires too many simulations to apply for cosmological analyses. However, simulation-based inference gives us a really nice insight, which is that inferring the posterior is just a density estimation problem. You have all of these samples of this joint distribution, and we want to estimate the probability distribution of the parameters given the data. So then you might be wondering, does that mean we can use the standard density estimation methods like kernel density estimation, like KDEs, or Gaussian mixture modeling? And the short answer is yes, you can. And that's what I did a couple of years after the ABC paper, where I applied, for instance, Gaussian mixture models to reanalyze a group multiplicity function analysis of HOD parameters by Manodeep Sinha. So you can see here, I'm showing you the posterior. This is the original analysis, and this is with simulation-based inference with Gaussian mixture models. I also reanalyzed the Boss power spectrum analysis in blue by Florian Beutler. This is the reanalyzed with independent component analysis, which is a slightly fancier density estimation method. And in both of these cases, there were sufficient simulations to do this. In the group multiplicity case, a function case, there was 20,000 simulations. And for the power spectrum case, there were 4,000 simulations. However, as you can imagine, there's some limitations to this approach. The group multiplicity function is only 8-dimensional. The power spectrum is only 37-dimensional. The bispectrum that I showed you is 1,898-dimensional. So scaling these methods to this high-dimensional problem is a real challenge. Fortunately, we can use new techniques in machine learning for density estimation that have been developed for generative models. So I'm going to briefly talk about what generative models are. And what better way to learn about generative models than to ask the world's most famous generative model, ChatGPT. So if you ask, can you explain generative models? ChatGPT tells you a generative model is a type of machine learning model that can generate new data that is similar to the data it was trained on. These models learn the underlying probability distribution of the training data. And that's the portion that I really want to highlight. So behind ChatGPT, DALL-E, Stable Diffusion, all those cool images and texts is a density estimation algorithm in the background. So let me give you an intuitive idea of what these generative models are doing. Here is the famous MNIST data set. This is a standard training data that people use for machine learning applications. It's these 28 by 28 pixel images of hand-drawn digits. So what we can do is train a generative model on this data set. And that's equivalent to estimating this probability distribution of these 800 different pixels. And then once you've trained this estimate, you can sample this distribution, and then you would get something that looks like this. You can see that even though this is an 800-dimensional distribution with really no real structure, if you just line them all up, it's able to derive images that look remarkably like handwritten digits. You can also use a generative model to train conditional probability distributions. So you can do something like, what's the distribution of all the pixels conditioned on the values of the central pixels? And then if you were to sample that and sample it so that we set the central pixel values to 0, in that case, we would only expect to get O's, since that's the only ones with no values in the center. And if you sample this, that's exactly what you get. So in our case, we don't care about pixels or central pixels or images. What we care about are the cosmological parameters given the galaxy clustering observations. So let me next give you a really brief explanation of what these generative models do in the background, because I want to explain that these are not black boxes, but specific techniques that achieve a very, very specific purpose. And what they do is they reformulate density estimation into an optimization problem. So the goal of training these generative models is to learn the hyperparameters of some very, very flexible model Q that best approximates the probability distribution we're interested, i.e. the posterior. And it does so by minimizing the KL divergence between the posterior and the model. So the KL divergence, I'm not going to go into these equations in detail. It measures the differences between the two probability distributions. And the really unique or neat trick here is that you can do this using Monte Carlo integration with samples drawn from this joint distribution, which, let me remind you, are samples that we can generate with a forward model. The only requirements really is that this model, Q of phi, has to be easy to evaluate and then flexibly expressive. So it has to estimate this high dimensional distribution. So you can imagine it has to be very flexible. And one popular model that was recently developed, although I've been told it's already outdated, is normalizing flows, which are these models that transform a Gaussian distribution into the distribution that you want using a series of invertible and differentiable transformation. So you can think of it as a really effective application of change of variables. And the advantage of this is that you can stack many of these different transformations, and it'll still be invertible and differentiable, and each of them are neural networks. So by adding more, you can make it more and more flexible. So let me give you some examples of how flexible it really is. This is in 2 dimensions. This is a Gaussian distribution of random points. And with just a few transformations, you can produce this double crescent moon shape easily. And here's an example in 3D space. These are 3-dimensional points. And just with a few transformations, you can make it into an airplane or a chair or a car. And again, this flexibility is important because we need to use it to estimate a high-dimensional probability distribution, in our case, the posterior. So now that you know how simulation-based inference works and how normalizing flows work, we can go ahead and apply it to the cosmological analyses that we're interested in. And this is the framework that I've developed called Simbig, which stands for Simulation-Based Inference of Galaxies. So the first step of this process is to generate training data using our forward model. So this is, again, sampling this joint distribution of parameters and observations. Afterwards, we can use that training data to train our normalizing flow. And then we take the measurement of the observations from the actual observations, plug it into the conditional distribution, and then you can sample parameter values, and that gives you an estimate of the posterior. So you know how the second and third steps work. So I'm going to focus now on the first step a little bit, give you a little more detail about that. So in Simbig, our forward model is targeted at the SDSS-BOSS observations. So we start again from M-body simulations from the Quixote suite. We identify dark matter halos, this time using Rockstar Halo Finder, which is a 6-dimensional phase space, uses 6-dimensional phase space information. Then afterwards, we populate the galaxies again with an HOD model, but it's a little more state-of-the-art. It includes assembly bias, concentration bias, and velocity bias. And the last step is we apply all of the survey realism of the survey into our simulation. So this includes the Redshift Space distortion that I talked about in the introduction, the geometry, the masking of the stars, and fiber collisions. So here is an angular distribution of the observations compared to the forward model. And I really want to highlight how in our simulation, we reproduce all of the little details that are in the observations, like these holes, these stripes. You can see the stripes also there. So we're reproducing all of these detailed systematic effects. Yeah.
That is what you see.
Left is what we observe. Yeah.
What did you feed your machine to get this?
The M-body simulations, the HOD model, the dark matter halos, all are a whole simulation pipeline.
That will produce the scores where you want them.
Yeah, that's part of our forward model where we actually simulate all of the systematic effects. Here's another view of a comparison of the two, this time in 3D space. I don't get to make a lot of simulations, so this is really exciting. you can see, I really want to highlight here that you can, the simulated forward model simulations really reproduce all of the little details in the observations very effectively.
Chang, if I can just to clarify, so.
Yeah.
So if they didn't, you would adjust your halo occupation distribution, for example, or you would adjust something in the part that's adjustable in order to make it match. That's what you're trying to do.
Yeah, so I actually forgot to mention that the training data spans all the different cosmological parameters and HOD parameters. So it's all these different realizations of the universe. So that allows us to do this comparison. So without further ado, now I can show you the actual cosmological constraints we derive from applying simulation-based inference to these simulations. And we can analyze, for example, the nonlinear galaxy power spectrum. And this is, I just want to point out that this is down to K of 0.5. Standard analyses are currently limited to 0.2. So this is going significantly deeper. And this is only possible because we use simulations. Here's the full posterior that we infer from the simulation-based inference. The top set of panels are the cosmological parameters again, and the bottom set are the HOD parameters. Like I said, we use a more sophisticated one, so there's a lot more parameters in the bottom now. But focusing on the cosmological parameters, I just want to emphasize that we are able to place precise constraints on the on sigma 8 and omega matter. These are the parameters that determine the growth rate of growth of structure. So these are our parameters of interest. So if we focus on these parameters and then compare it to Misha Ivanov's recent paper using perturbation theory, we can see that we're able to constrain sigma 8 by 27% tighter than the standard method. And this is by exploiting cosmological information on nonlinear scales. And again, this is important because this sigma 8 value goes into the F sigma 8 measurement of growth of structure. But of course, we can go beyond the galaxy power spectrum with this approach. We can also analyze the galaxy bispectrum down to K of 0.5. And when we do this, we improve the sigma 8 constraint by 60%. So we double the precision of the cosmological constraints. And this is by exploiting information both with higher order statistics and nonlinear scales. So I just want to emphasize that this factor of 2 improvement is very significant because that's equivalent to observing a survey that's 4 times the volume. And we can also analyze non-conventional statistics like wavelet moment statistics, and we find even more cosmological information from these. And so right now, the goal of Simbig is to apply these cosmological analyses to any galaxy clustering statistic. And in addition to the ones that I've mentioned so far, I'm leading a collaboration right now with these folks here that are looking at the Mark power spectrum, the skew spectrum, void statistics, and also neural network compressions of the galaxy field. So our goal is to extract all of the cosmological information of galaxy surveys using simulation-based inference. So in the last couple minutes that I have, I want to give you a quick update on the status of the next generation of galaxy surveys like DESI and PFS, which I've led, and tell you about my plans for the analysis that I plan to do using the transformational data sets that they're going to produce. So DESI, as many of you might know through Nikhil, is the Dark Energy Spectroscopic Instrument. It's currently observing on the Mayall 4-meter telescope, and it'll operate for the next 4 years. And if you were to look at its focal plane, this is what it would look like. You would find all of these robotic fiber positioners that's capable of measuring 5,000 spectra simultaneously. And it'll provide spectra over the optical wavelengths with medium resolution. Here's a short video of how these fiber positioners actually work. It's kind of cool when they all move coherently. Anyway, with this technology, DESI is going to observe 40 million galaxies, all the way out to redshift of 2.1. And I just want to point out, as a builder in the DESI collaboration, I will have full data access for this survey. And in particular, I'm very excited about the Bright Galaxy survey in DESI, and not just because I led the survey for the past 3 years, but because it'll observe 15 million galaxies at low redshifts during the dark energy dominated epoch. And what it'll produce is a magnitude limited sample of galaxies that goes down to R-band magnitudes of 19.5. So this is 2 magnitudes deeper than the SDSS main survey. And it'll also produce a fainter sample down to beyond R of 20. And it's going to cover 1/3 of the sky. And also, in addition to this, with work that I've been doing with James Kwan, who's now a graduate student at UC Santa Barbara, we've developed all of the tools to measure the detailed physical properties of these galaxies, like their stellar mass, star formation rate, metallicity history, for each of the 15 million galaxies from their photometry and spectra. So this will be a really effective sample, not just for cosmology, but also for studying how galaxies evolve. And so for the purposes of Simbig, the reason why BGS is so exciting is that it'll provide a high density sample that's an order of magnitude larger than previous surveys. So here I'm showing you the number density as a function of redshift for BGS in the solid line here. And I'm comparing it to 2 other previous surveys, SDSS and Gamma. And so you can see that we have significantly higher number density throughout our entire redshift range. And in fact, in its first year, BGS is already, this is the first year out of a 5-year operation. BGS is already ahead of schedule and observed 33% of the survey. I'm showing you here the angular projection of the sky, and I've labeled in the different colors the portions of the sky that we've already observed. So we've already made remarkable progress in the first year. And in fact, there was recently a fire in Kitt Peak National Observatory back in June. However, thanks to the heroic efforts of the firefighters and also the DESI team, we're back online and we've observed over 2.5 million spectra since the fire. And in total, we've observed over 17 million galaxy spectra. I'm also very excited about the Sumire Prime Focus Spectrograph, PFS, Cosmology Survey. This is a survey that I'm currently co-leading. And this survey will observe on the 8.2 meter telescope, a Subaru telescope, starting next year. And it's also equipped with robotic fiber positioners, and it'll be able to measure the spectra of 2,400 galaxies simultaneously. And it'll provide spectra with broader wavelength coverage than DESI with comparable resolution. And I just want to point out that as a continuing participant, I will also have access to data from PFS. So let me give you a quick video, show you a quick video about how PFS operates. These are the photons from a distant galaxy shooting through the universe. I think more surveys should have these types of instructional videos. It's pretty awesome. And here's the Subaru telescope that's going to collect these photons. You can see it hitting the 8-meter mirror in the telescope, then going to the focal plane full of these fiber positioners. The light then goes through these fibers into the spectrographs, the 3 different arms of the spectrograph, and then we can collect that measurement and then combine it into a spectra. And so using this information, we can unveil the mysteries of the universe. And we're going to do that by observing 5 million emission line galaxies out to redshift of 2.4. So I want to point out that this is at higher redshifts than the DESI survey, so it'll provide a longer redshift baseline. And currently I'm working with Yuka Yamada, who's a student at University of Tokyo, in finalizing the target selection for the survey. So I've been focusing a lot on the redshift range and the number of galaxies. And the reason why this is important is because the redshift range gives us the redshift baseline for measuring the growth of structure. And the number of galaxies tells us the precision to which we can make these measurements. So I'm showing you here again the current constraints from existing observations. And this is what we expect with DESI and PFS. So you can see that we do significantly better than existing observations, and we'll be able to precisely distinguish between different cosmological models. Now for neutrino mass, this is the current limits from cosmology, 0.13 eV. With DESI and PFS, we'll be able to measure the sum of neutrino masses with 0.03 eV precision. So if the neutrino mass are minimal and the hierarchy is normal, we'd be able to exclude the inverted hierarchy at 1.5 sigma. Of course, all of this is with the standard analyses. And my plan is to use simulation-based inference to extract all of the information, and this will double the precision of these constraints. So for the growth rate of structure, this is the constraint from DESI and PFS, and this is what Simbig will, we expect Simbig to measure. I zoomed in because people complained that they couldn't see the width of the orange lines. So it'll be much, much more precise measurements of the growth of structure that'll allow us to precisely distinguish between different cosmological models with unprecedented precision. And I just want to emphasize again that the improvements that we get here from doubling this precision is equivalent to running DESI and PFS for 15 more years. So this is a really significant improvement. And for neutrino mass, this is the constraints we would get from DESI and PFS. And this is what we expect by applying Simbig to analyze it. So again, if the total neutrino mass is minimal and the hierarchy is normal, we'd be able to exclude the inverted hierarchy by more than 4 sigma. So let me summarize some of the main points here and finish. So galaxy surveys provide us with the distribution of galaxies, which encodes a lot of cosmological information that we can use to probe the nature of dark energy and neutrinos. And if we analyze non-linear scales with higher order statistics, we can extract much more cosmological information than what's being used in current analyses at the moment. And one way to do this is by using simulation-based inference and machine learning, which I've demonstrated on existing observations can dramatically improve the constraints. And so my plan in the future is to use this framework to extract all of the cosmological information that will be available in the galaxy surveys of the next decade, starting with DESI and PFS, but also Rubin, Roman, and all of these other surveys that are currently being planned at the moment. Thank you. Frank, you missed your shout out.
All right, so let's see. So we'll go in order.
About the simulation-based inference. Do you, in order to achieve the kinds of accuracy needed for the state-of-the-art neutrino mass constraint, are you worried? How much are you worried about baryonic effects, and what's the role of hydro simulations?
That's an excellent question. I'm definitely concerned about baryonic effects. However, the forecast that I'm showing you here is only going down to K of 0.5, where the effect is smaller than, for instance, in weak lensing, where you go down to much higher Ks. But we're actually looking into this right now, where we're using camels, which you're familiar with. So using these hydro simulations and then looking at the baryonic effects as a function of both cosmology and the baryonic input parameters of the hydro sims. So with that, I will be able to have much more control over the baryonic physics and ideally marginalize over it. So that's sort of the next developments of Simbig in the forward modeling pipeline. Yeah.
Yeah, thank you for the presentation. I have a question regarding potential future limits from laboratory experiments and how this might test cosmology. So if you measure the neutrino mass with laboratory experiments and you find something that is either inconsistent with the limits that you're setting, or if, how do you then go forward? What can you learn about cosmology? And what are the model dependencies in the limits that you're currently setting?
That's an excellent question. And I think you're definitely listing the most exciting scenario where there would be this conflict between the constraints we get from cosmology and the laboratory experiments, because then that means that there's something in how we model neutrinos in cosmology that is clearly not, that we don't understand. So I think, we would have to re-examine all of our neutrino simulations in cosmological simulations and then see how we can improve from there. Yeah, that would be a really exciting avenue of research.
Thanks. So you have a lot on your plate, but let me just ask you about SphereX, which you didn't mention. How will it be useful? It goes farther into the infrared and not as many galaxies, but much.
Yeah,
more.
so I didn't get the opportunity to give a shout out for all the surveys, but SphereX would also be important and also would be an excellent observations to apply forward modeling in, because there's a lot of systematics there in terms of the redshift precision and the spectroscopic redshifts that you can get that is easier to simulate than to account for in the cosmological analyses. So really, I think that's also a survey where this approach would really shine.
Okay. All right, Laura.
Yeah, so you found a tighter constraint on sigma 8. Do you want to comment on the comparison between large scale structure and CMB measurements of sigma 8?
Yeah, I didn't include anything about that, the S8 tension. So this is, for those of you who aren't familiar, this is that if you measure sigma 8 or the combination of sigma 8 and omega matter with CMB versus weak lensing, there's this, let's say 1.5 sigma, 2 sigma, it changes pretty periodically, tension between the two measurements. So for our constraints, we actually find no tension with CMB, but it's still a little preliminary because it's not, the constraints aren't tight enough to definitively say that we disagree with weak lensing either. But yeah, that is something we did comment on in the paper.
Okay, any questions from the Zoom world? No, any more questions from the room?
Yeah, thanks. I have another version of a dice case question. You talked about improvements in the cosmological parameters by going to smaller or nonlinear scales. And you mentioned a factor of 2 improvement in going from K of 0.2 to 0.5 H. Yep. So I think that 0.5 H, I think that corresponds to 3 megaparsecs, kind of the scale of a galaxy cluster.
Yeah.
Right. And so that's when stuff gets hard, a lot of nonlinear effects. So my question is, what do you see about the potential gain versus the challenges of going, say, another factor of 5 in smaller scales?
So I think that's an excellent question. And we can go deeper, but of course, we would also have to make our models of the galaxy halo connection more flexible. So at some point, there is this trade-off of you don't really gain that much because you would have to marginalize over so much uncertainty in the baryonic physics of the connection. But one of the sort of longer term goals that I have is, oftentimes in cosmology, we treat galaxies as if they're point particles tracing the matter distribution, but we know a lot about galaxies. And we have all of these hydrodynamical simulations that can reproduce the different observations. So that means we can use them to set sort of model priors on what we expect from the baryonic physics. And that would actually further tighten the cosmological constraints. So that's sort of the longer term goal. But of course, it would require a lot of work in, understanding the hydrosims and then using that to develop models of the galaxy halo connection.
I had a related question, which I'll go ahead and ask since Jeff asked that. Since you're using simulations to help guide the analysis, does it matter what your minimum particle mass is? Because you need to do gazillion simulations. Let's be technical, and often the particle masses just aren't realistic.
Yeah, so that's definitely that's an excellent point, and that's one of the reasons why we need to use these machine learning techniques, because they're more efficient than standard methods. So if we could run, a gazillion simulations with infinite resolution, we could just use ABC, the simplest method, and we would be done, and that's it. But in this application, for example, we're only using 2,000 n-body simulations. So that's a relatively small number and equivalent to the usual budget of standard analyses. So in that regime, I think we can push the mass resolution down to the limit where it's not a concern. But we've also done some tests in this case where we've made sure that the resolution, we have a higher resolution simulation. So we validated against that to make sure that the clustering is the same, at least down to the scales that we've analyzed. So this is a check that we have to do. And also it depends specifically on the galaxy population that you want to analyze. So for LRGs, the requirement is different than emission line galaxies, which are in lower mass halos.
All right, so let's wrap it up here. Thank you, Chang.